So the last word that I would like to talk about this week related to population is equilibrium. So to recap, earlier this week we talked about how the population of a species could be affected by abiotic limiting factors. So these are non-living things that affect the population of a species. So things like how much space there is, how many resources there are in the area, and what the climate is like in the area, and many other abiotic things will affect the population of a certain species. And then in the previous lesson, we talked about biotic interactions. And the biotic interactions are going to also be limiting factors to the population of a species. So how many predators you have in the area, that's going to affect your population. How much prey you have in the area, so that's like your food source, that's going to affect your population as well. Also the amount of competition. So you have this prey, you have your food source, but then how many other species are there that are also going after the same food source as you? Well, that's going to affect your population. The presence of symbiotic species. So you may have species that are mutualistic with you, so you help each other. So with those species around, that might help your population. On the other hand, you might have species that are parasites to you, so they harm you, so that's going to affect your population as well. And then one thing we didn't talk too much about, but it was part of your assignment the week before, actually, it was invasive species. So in the coral reef simulation, you had to insert an invasive species into the coral reef ecosystem and then see how that affected all the populations. That's going to be, we'll focus on invasive species more next week. Okay, but that will definitely affect the population of other species as well. So I'm going to focus on predator and prey in the next slide. So this graph here, this is like some famous data actually, because it goes all the way back to 1845. Okay, and my graph here goes up to 1935. So that's a 90-year span, and this is real data. And it's kind of like the earliest, or some of the earlier forms of population tracking data. It comes from the Hudson Bay Company. So they were involved in what we call the fur trade back during this time when the settlers from Europe went to North America. One of the big businesses there was fur trading. Two of the animals in which they got furs from were hares and lynx. So hares are in blue on this graph and lynx are in red. A hare is kind of like a rabbit, and a lynx is a kind of related to a fox. So the predator would be the lynx and their prey would be the hare. And what this graph shows is how many I guess how many coats of hare and how many coats of lynx the Hudson Bay Company was able to get from the hunters, or the trappers we call them, who went to North America. And they would trap these animals and sell the furs to the Hudson Bay Company. And this just graphed how much they trapped each year. And so it's not exactly the population of the hare and the lynx, but it's closely tied to the population, because a higher population means they could do more trapping. So the key feature about this graph is that, well, I'll start with the blue. Blue is the hare, and you see that the hare population kind of cycles up and down and up and down and up and down. So hares kind of have this natural cycle where their population is going up and down. And it looks like the lynx has that as well. The lynx population is up and down and up and down and up and down. But what I want you to notice is that the red graph is slightly shifted to the right compared to the blue graph. So just look at this peak right here. This red peak for the lynx happens just a couple years after the blue peak happened for the hare. And then same with the bottoms. So the hare population bottomed out here. And then just a couple years after that, the lynx bottomed out. Okay, so it's like the red graph kind of follows the blue graph. It's a bit more clear on the right-hand side here. So look, we have a blue peak, and then slightly after a red peak. We have a blue bottom, and slightly after a red bottom. And then a blue peak again, slightly after that's a red peak. So yeah, it's like the lynx population graph is following the hare population graph. And that's like this is like a classic example of a predator-prey relationship. So when there's more prey available, when there's more hare available, then the lynx population starts to go up. But when there's less hare available, when the hare population goes way down, then shortly after, the lynx population goes down. Okay, so this is just showing you that the population of one species is closely tied to the population of another species. So they always try to have this sort of a balance. And that's the word that we'll talk about a bit later, equilibrium. Another example of how one population can affect another. So the previous example with the hare and the lynx was predation or predator-prey. Well, mutualism, that's when two species help each other. Well, the population of one species is going to affect the population of its mutualistic species as well. So here's an example. In the past couple of decades, farmers and scientists have been concerned about colony collapse disorder, a sudden disappearance of worker bees from bee colonies. Bees are important pollinators of many crops such as coffee, avocados, limes, or lemons and limes. A large drop in the bee population will lead to a drop in these crops. But fortunately, cases of CCD, colony collapse disorder, have declined over the past 5 years. So this is a picture of a bee on a coffee plant. And so bees help to bees get food from the coffee plant, but then they also help to transfer the pollen from the coffee plant to other coffee plants so that the coffee can reproduce. And so that means if the bee population were to suddenly collapse, then we're going to have less pollination of the coffee plant. So less bees is going to mean less coffee and all the other kinds of plants that bees help to pollinate as well, such as avocados, lemons, and limes. So, yeah, one population can definitely affect the levels of a different population of a different species. So this word equilibrium, which is a topic for the lesson, here's the description. Equilibrium is when the biotic and abiotic factors in an ecosystem have naturally reached a balanced, stable state. If like a new ecosystem starts, if you let that ecosystem kind of just sit there undisturbed for a long period of time, then naturally they're going to reach some sort of a balance. Okay, that balance will involve some cycles, the up and down cycles, like the hare and the lynx population that I showed you. But over the long term, those cycles will be pretty predictable and pretty stable. And that balance that they achieve, we call that equilibrium. Okay, and Equilibrium can be disturbed. So something can happen and disrupt an ecosystem from equilibrium. So this can be something like a natural disaster can cause a disruption in the equilibrium. A disease can come in and disrupt the equilibrium, or what we're more concerned about recently is humans and the human activities disrupting the equilibrium of ecosystems. So how does an ecosystem respond to this disruption? Well, different things could happen. Here's just three possibilities. It may just recover to the same equilibrium that it was before. Okay, so maybe like a one-time event happened, like a natural disaster, a one-time event, but then slowly the ecosystem builds back up to the same equilibrium it had before. It could find a new equilibrium, so maybe this is not a one-time event, maybe this is like a permanent change. Well then, the ecosystem is going to have to adjust to that, and they may strike a new balance, a different balance, and find a new equilibrium. Or maybe this disruption is just going to cause chaos and cause the equilibrium to collapse, the ecosystem to collapse. That would be the worst case scenario. So this is one of the gizmos, just to show equilibrium. And this is just one food chain. So there's hawks, snakes, rabbits, and grass. And the populations shown with these numbers here. And you can decide if you're going to have healthy populations or diseased populations. But we'll stick to healthy right now. So if I push play here, the graph of all four species is shown, and you'll see that they're fairly balanced. They stay around the same level. This axis is labeled as percent of balance. Percent of balance. And right now it's showing 100% for all of them. So that means it's just being balanced. That's because I just started out with the ideal conditions. Now, let's say something happens and for whatever reason, we start with a lot fewer snakes. So there's 278 snakes. I can click this minus sign, make the snake population go way down, and then click play. What's going to happen on the graph here? Okay, well there's the beginning. I click play and then hit pause. So the snake population started out a lot lower than normal because I set it that way. But without many snakes there, the hawks that eat it, well, a lot of the hawks will start starving because there's not enough snakes to eat. That's why you see the blue graph for the hawk go down. And how about the rabbits? Well, the rabbits normally get eaten by snakes. So if there's less snakes, then the rabbits have fewer predators. So the rabbit population you see goes up. At least at the beginning, it goes up. Well, what happens when there's more rabbits? When there's more rabbits, then there's more rabbits eating more grass. So the grass population will probably go down. And the graph shows it goes down. Okay? However, if I keep letting it play, you'll see that over time, the ecosystem kind of recovers and goes back to equilibrium. So that change I made, reducing the snakes by a lot, that was like a one-time change. The ecosystem eventually recovered. I could make more of a long-term change and introduce a disease to the snakes, like a long-term disease to the snakes. It's going to affect the snakes for a long time. Well, then what happens to the graphs? So now that I have kind of more of a permanent change in there, the ecosystem had to kind of adjust, and they found a new sort of equilibrium. Okay, so the populations have steadied out again, and they found a new kind of equilibrium there. Okay, so I'm out of time here, so what I'm going to do is make a second video to finish off this lesson. So I'll see you in that one.